Hey everyone, this video is dedicated to the strategies you want to have in the back of your mind as you approach these problems that are involving Newton's second law. So we're going to go over the strategy, the item by item list of things you should be doing, and then we'll look at an example problem to see how it is applied. So whenever you come across a problem where you're going to be applying Newton's second law, in particular math problems, all right, though this is also helpful for more conceptual questions. For math problems, it's vital that you are doing these 5 different steps. They are all going to help you be successful in solving the problems. So the first step is to draw a free body diagram. All right, remember those are those dots that we're making, and then we are drawing arrows to represent whatever forces are acting on things. This is a crucial step because the second law problems are all about understanding what forces are acting on things and in what direction. If you cannot do that, and if you cannot represent that visually as a free body diagram, the rest of these steps doesn't matter. You're not going to be successful. The first thing I ask when a student comes up to me and says, hey, Thrasher, can you look over this problem? I'm having trouble. The first thing I'm going to say is, let's see your free body diagram. Okay? Even if the problem doesn't ask for it, you need to be doing step 1 every single time. All right? After you've made your free body diagram, like we've done for motion, we want to make sure we understand and we know what our positive and negative directions are going to be. As a reminder, to the right is usually considered positive by convention. Similarly, upwards is conventionally the positive direction. I like to draw things like this on every problem just so it's super clear, especially if you want to buck some trends. If you like saying to the left is positive, you can do that, but I would highly recommend you label it so whoever is looking at the problem understands that's what you're doing. Otherwise, they might get confused. So you've drawn your free body diagram, you've labeled your positive and negative direction. Now, step 3 is when you actually apply Newton's second law. And to do that, you should write out all the forces that are acting in that direction. Remember, these are vectors, so you can't mix and match forces in the x direction and forces in the y. You might have to apply the second law twice, and we'll definitely get some experience with that. But start in the x direction, list all the forces in the x direction. Then if you need to, look at the y direction. All right, you set all those forces, you add them up or you subtract them, and then that's going to equal ma. That's what the second law says. Step 4 is really to figure out how we need to approach the problem based on what the second law is going to be equal to. What I mean by that is we know the sum of the forces is equal to ma. Well, if the object is accelerating, once we have our list of forces, we, of course, know to equal that to the mass of the object times its acceleration. The object, however, might not be accelerating. If something is either staying at rest or staying in constant velocity, the term is equilibrium. And that can be helpful because if something is not accelerating, well, this would become 0. And for objects in equilibrium, the sum of the forces is equal to 0 because any mass, anything, times 0 would be 0. It just helps us be aware of what our second law should ultimately be equal to. Anyway, once you have those equations set up, of course, then you should do any kind of math you need to do. It might be arithmetic, multiplying numbers. There might be some algebra involved, but then try and figure out what the question is asking you to solve for, and then, well, solve it. So let's look at an example. Here I have a problem that says a student pushes straight down on their 1.6 kilogram physics textbook with a force of 11 newtons. Calculate the normal force acting on the book if it remains at rest. Okay, so we're going to go through our item by item kind of checklist, our strategy to solve this problem. Step 1 is to draw a free body diagram. Okay, it's asking about the book, the normal force on the book. So we're going to draw a free body diagram for the book. I like labeling them. It just makes it super clear, especially in the future when we might have multiple objects that we're going to be analyzing. Okay, but there's my dot. The dot represents the book, forces that are acting on it. Well, I know that the book has some weight because we're here on Earth, so I'm going to draw an arrow that's acting downwards. That's W. I made my dot kind of obnoxiously large because there's another downward force, this pushing force. All right, it says the student's pushing straight down. You could label that P for push. I'm going to label it F just because that's what that picture on the left is already labeling it. So that's the force pushing it downward. And the table is acting as a support. There is some normal force acting upwards. Okay? So there's a good rough draft of a free body diagram for this book. It has weight, you're pushing down on it, and the table is supporting it. Okay, notice I don't have any forces in the x direction, so we're just going to focus on the vertical forces. Step 2, let's make sure we're clear on the positive and negative direction. Like I said, I'm not really going to worry about the x direction since no forces are acting that way. I'm going to say upwards is positive. So any force acting upwards is in the positive direction. Any force acting downwards is in the negative direction. Step 3, let's now write out the sum of the forces in the y direction. Here we go, sum of the forces in the y direction. Well, there's 3 of them in total, and I'm saying upwards is positive. So there's the normal force, which is positive, because it's acting upwards right here. Then there's the weight. Since the weight is acting in the opposite or negative direction, I do minus W minus F for that pushing force. That equals, the second law says that's always going to equal the mass times the acceleration in the y direction. Next step. Is it accelerating? Well, no, it says the book is remaining at rest. You might sometimes have to read these problems once or twice or 3 times to make sure you get all the necessary info. If it's staying at rest, the acceleration by definition is 0. So this term right here is going to be equal to 0. By the way, remember, the weight of an object is always equal to mg, so I'm going to plug that in over here. So I have the normal force minus mg. Oops, I meant to do that in orange, oh well. Minus F equals 0. Well, it's asking for the normal force. So I'm going to just have N equals. I want to swing these other 2 things to the other side. Just doing some basic algebra. That's going to be mg plus F. All right. Well, mg, that's the mass times 9.8. That's 1.6 times 9.8 meters per second squared, plus the pushing force, which was right here, 11 newtons. Plug that into your calculator, 1.6 times 9.8 plus 11. I get 26.7 newtons. I just rounded after one spot. We are not strictly following sig figs for this course. I would just round after 1 or 2 places and you're fine. That's equal to the normal force. So there's our answer. Couple things I want to mention though before I end the video. The first thing, I have a lot of students who, when they get to the plugging in stage, they go back to, 9.8. That's that acceleration due to gravity. And they correctly remember that we would always do this, minus 9.8 meters per second squared. Notice I did not plug in a negative, and that's correct how I did it. Before, we had these pre-written equations, things that look like this. And we always use these basic equations. And so, if things were positive, we'd plug in positive numbers. If they were negative, we'd plug in negative numbers. But now, for second law problems, notice we wrote our own equation. And we already took into account whether something was plus or minus. We are already saying that this term is acting downwards because we wrote minus here. If you plugged in a negative number for 9.8 here, that would actually be making the presumption that this weight is acting upwards, which is both conceptually wrong and would give you the wrong answer to this math problem. So now don't double dip with your negatives. All right, as you write the equation for the second law and you put it as minus that force, well, now you don't have to worry about plugging in a negative 9.8. Vectors are crucial. Okay, we have to make sure we understand that. The other thing I want to point out is that, yeah, this is a math problem, and you were ultimately getting a math solution, but this math problem makes sense. Okay? If you have a book and it's sitting on the table is supporting that book. Well, if the book isn't moving, that support must be enough to support the weight of the book and however much you're pushing it down. Remember Newton's first law, an object at rest will stay at rest unless there's a net force. Well, the book is staying at rest, so there can't be a net force. So the only upward force must balance the downward forces. All right? Just as important as these math problems will be the conceptual questions we come across that also involve the second law. Okay? And it should make sense that if forces are balanced in this case, well, the upward and the downward forces should be balanced. And this will continue on even when things are accelerating. We should be able to conceptually understand that. And we'll get to that. All right, thanks for watching the video.